Hey everyone! In this video, Michael will be going over problem 9 from the 2024 Euclid contest. This is our fourth video in the problem solving series. Problems 9 and 10 are the hardest problems on the entire contest, so we'll be splitting them into two separate videos. Get ready for a challenging problem solving experience!
Okay, I'm Michael, and we'll proceed by problem 9 from Euclid 2024 contest. So what we have is an ant walks along the x-axis. It can either move to the right or to the left by 1, and it takes a certain amount of steps to get a certain distance. So for part A, it must take 9 steps and reach a distance of 5. And we can first start by finding how many steps to the right it takes and how many steps to the left it takes. So notice the sum of the number of the steps to the right and the steps to the left is 9, and their difference, which is the distance that the ant covers, is 5. And you can solve that, and you can easily see that you must take 7 steps to the right and 2 steps to the left. That's the only way for you to, using 9 steps, reach a distance of 5. So in total, 9 steps are taken. Out of these 9 steps, you can choose any 2 steps to be to the left. And the rest of the 7 steps must be to the right. Or you can choose any 7 steps to the right and the rest of the steps are to the left, and both of these value equal 36, which is our answer. As this is 9 times 8 over 2 times 1, that is equal to 9 times 4, which is 36. Now let's proceed by part B. So we need to determine the number of sequences for which C, which is how many times the ant changes the direction, is even. So n equals 9, it must take 9 steps and it must cover a distance of 3. You can do the same thing as part A, where you evaluate how many steps are taken to the right and how many steps are taken to the left. Notice the ant must have taken 6 steps to the right and 3 steps to the left. That's the only way possible to get a distance of 3 while taking 9 steps. And now just determining raw the number of sequences for a set C is hard, right? So instead of doing the hard way, we can find an easier way. And notice that when C is even, the number of times the ant changes direction even, that means the ant must have ended in the same direction that it has started in. The ant, if it changes direction once, the direction is changes, right? But if it changes direction twice, then the direction goes back to the original. And if it changes direction 4 times, same thing, right? That's just changing direction twice and changing direction twice. So the direction is the same. So for C to be even, we just need to find the number of sequences when the first step and the last step have the same direction, right? So for example, if it's if you start right and then you change 3 times, that's not the same direction because you started right and ended left. So that's when C equals 3, that's bad. C equals 4, that's when you start right and end right, and that is good. Now we can split this into 2 cases. One case is when you start right and end right. and that means the last step is also. And here we can see that if the first step is right and the last step is right, we are making a total of 9 steps, right? That means there are 7 steps left. And of those 7 steps, 4 steps are to the right, because we are making a total of 6 steps that are going to the right, and we have already used 2 of them here, right? So that means there are 4 steps to the right that are remaining, and obviously we haven't used any steps to the left yet, so 3 of the 7 steps are to the left. And to compute the total for this case, that's just the same thing as last part, right? It's just there are a total of 7 steps. Of the 7, 3 can be to the left and the remaining 4 to the right, or 4 of the 7 are to the right and the remaining 3 are to the left. So it's either 7 choose 3 or 7 choose 4. Both give the same value of 35. And case 2 is when the first and last step is to the left. Right? We can do the same thing here. It's just L for left, R for right, L for left. And then there are still 7 steps left because 9 steps are taken in total. And of the 7 steps, 1 is to the left because there are 3 in total to the left, and you've already used 2 left steps here, so there's 1 remaining left step. And 6 steps are to the right. So we can do the same thing as we have done in part A and the last case. Of the 7, 1 must be to the left, so it's either 7 choose 1 or you can do 7 choose 6. Both give the same value of 7. So in summary, these are the 2 possible ways for C to be even, and in total that gives us 35 plus 7, which is 42 ways. So in total there are 42 ways for C to be even. So now let's proceed by part C. So we need to find the number of sequences for which C is even, and you need that to be equal to exactly half of the sequences in total. So we can do the same thing as part B, right? So we need the start and the end step to be equal, right? And we can do that in 2 cases, similar to the last question. So the first step, let's just assume, so there are a total of D steps, right? So let's just assume we are taking X steps are to the right. Here, X is just an arbitrary variable, and it can be anything. And there are D steps. Sorry, there are N steps in total. So that means N minus X steps are to the left. And the ant must end at X equals D, right? So the total distance covered by the ant is X steps to the right minus N minus X, because that's how many steps are to the left. Each step to the left subtracts 1, so you subtract by N minus X. That is equal to 2 at X minus N. That's the total distance you have covered, so that is equal to D. And that means that 2x minus d is equal to n. Right? Automatically, x plus n minus x is equal to n. So automatically, n steps are taken, right? So x basically can be anything, and x must satisfy that 2x minus d equals to n. Now we can do something similar to part B, where we find the number of sequences, because we are given this equation, right? We are given that the number of sequences in total, half of that is equal to the number of sequences where c is even. So let's convert that equation from words to numbers, right? And then we can solve for n in terms of d, or d in terms of n, right? So yeah, the strategy is to just convert that into numbers. So case 1, similarly as the last time, there are 2 cases, right? So case 1 is when the first step and the last step, same as last time, they are to the right. So there are n steps in total, and we can do this like right, r for right? We've already used 2 steps, so there are n minus 2 steps remaining. Of the n minus 2 steps, we are making a total of x steps to the right. That means there are x minus 2 remaining. Right? So the total value of this case, we can just evaluate that, same as last time, is n minus 2. Of the n minus 2, you can choose x minus 2 to be steps to the right, and then the remaining are going to the left. We don't need to like have a second like expression for this. 1 is enough. And case 2, the first and the last steps are to the left. So here it's like L for left, and there are n steps in total. We have already used 2 of them, and that means there are n minus 2 steps remaining. And you're going to take x steps to the right? And because you haven't used any of them, there are still x steps to the right remaining. So the expression for this case is just n minus 2 choose x. Because of the n minus 2 steps remaining, you're going to be choosing x steps to the right, and then the remaining steps you didn't choose are going to be to the left. So the total c even is just n minus 2 choose x minus 2 plus n minus 2 choose x. This works for n at least 2, right? If n is 1, then it doesn't work, because it doesn't make sense if there's like 1 step to the right, but then you're going to choose 2 of the 1 steps to the right. That doesn't make sense, right? So that's why it doesn't work if n is equal to 1. We will address that problem later. So this is equal to half of the total number of sequences. So n minus 2 choose x minus 2 is equal to half the total of the number of sequences. Well, plus n minus 2 choose x is equal to half the total number of sequences. And that's just of the n steps. You're just going to be choosing any x of the n steps to go to the right, and the remaining steps are going to be going towards the left. So yeah, so now we have produced an equation in numbers instead of words. That is good. And there are no other equations given. And when you have one equation and you need to find a relation between n and d, you simplify that equation. So we can use the formula for factorial for choose using factorial. So n minus 2 choose x minus 2, that's just n minus 2 factorial over x minus 2 factorial times n minus x n minus 2 minus x minus 2, that is equal to just n minus x factorial plus n minus 2 factorial over x factorial times n minus 2 minus x factorial is equal to half of n factorial over x factorial times n minus x factorial. And from now, we have this like kind of complicated equation. We want to simplify it so we can cancel out some things, and notice that a lot of things are equal, right? So we can just make more things equal to that thing, and after that we can cancel it out. So notice in the denominator there's like n minus x factorial, n minus x factorial, and n minus 2 minus x factorial, right? We want to cancel out n minus x factorial. So what we can do is we can make the n minus 2 minus x factorial to become a n minus x factorial. So what we can do is this one stays the same. So we can multiply both sides by n minus 1 minus x times n minus x. Notice n minus 2 minus x factorial times n minus 1 minus x times n minus x. Those two numbers are just the two numbers that are ahead of, that are like that are next to n minus 2 minus x factorial, right? So that's just equal to n minus x factorial. And that is equal to n factorial over 2x factorial n minus x factorial. So now we have n minus x factorial in the denominator for all three. So we can just multiply both sides by n minus x factorial to cancel. And we want more things to cancel, right? The more things that cancel, the better, right? So now that we have canceled n minus x factorial, we can do, we can further cancel out x factorial, right? So notice we have two instances of x factorial, so we can just make the two x factorials like, yeah, we can just make the two like x, we can just make the x minus 2 factorial equal to the x factorials. So what we can do is we can multiply both sides of this one, n minus 2 factorial, over, we can multiply both sides by x minus 1 times x, right? And x minus 2 factorial times x minus 1 times x is just x factorial, because x minus 1 and x are the two numbers after x minus 2 factorial, plus n minus 2 factorial, n minus 1 minus x times n minus x over x factorial is equal to n factorial over 2x factorial. So now we have both sides, Both sides have x factorial, so we can cancel by multiplying both sides by x factorial. Now we can cancel even more things. We want to cancel all factorials. So notice we have n minus 2 factorial twice, and we have an and we have an n factorial. So we can make the n factorial become a product of n minus 2 factorial and n minus 1 and n. So we have these stay the same. It's equal to, we want to make it a product of n minus 2 factorial and other things. So that's just n minus 2 factorial times n minus 1 times n, as n minus 1 and n are the two numbers after n minus 2. Right? So now we have n minus 2 factorial on all three of them, so we can cancel that. Now we have canceled a lot of things. So now we just have So now we just have x minus 1 times x plus n minus 1 minus x times n minus x. That is equal to n minus 1 times n. So now this is just a quadratic, right? So now what we can do, this is just a quadratic. So what we can do, we can just, it's not that like hard to just expand both sides. And notice that like there are many like small terms that are like the same, right? So they're just going to cancel. So it's not a bad idea here to just expand both sides. So we have x squared minus, this becomes x squared minus x plus, and we can find the value of n minus 1 minus x times n minus x. That's equal to n times n minus 1 minus x times n minus 1 minus x. That's equal to n squared minus nx minus xn minus x plus x squared. So if we add that, we can move that there. So that's equal to n squared. Sorry. That's equal to n squared minus n minus nx twice. So that's minus 2xn minus x plus x squared. That's equal to n minus 1 times n is just n squared minus n. So and this is over 2, sorry. Because the 2 didn't cancel, sorry. So now we can combine like terms basically. That is not that hard to do. And notice that notice that there are plenty of like terms. So it's just n squared minus 2xn minus n plus 2x squared is equal to n squared minus n over 2. So we can multiply both sides by 2 to get rid of the fraction. So then it's like 2n squared minus 4 nx minus 2n plus 4x squared is equal to n squared minus n. And we can move all, now this is a quadratic, right? So we can just move all of them to the same side. So we have the n squared moves to here. That cancels with a 2, so it's n squared minus 4nx. And the minus n, it decreases a 2 to a 1. So it's minus n plus 4x squared is equal to 0. So now notice that these three terms form a perfect square. And this is not just any perfect square. This is what we have previously evaluated for 2x minus d to be equal to n. Well, 2x minus n is equal to d, right? So this is 2x minus n squared minus n is equal to 0, right? This is not just any perfect square. We know that 2x minus n is equal to d. We have already found that above. Recall that. So d squared minus n is equal to 0, so d is equal to n. Well, d squared is equal to n. So now n is less than or equal to 2024, and d is greater than or equal to 0. Now recall that this only works if n is at least 2, right? So now we can just do like d equals 1, n equals 1. This doesn't work because n is not equal to 2 here, right? But if d equals like 2, then n equals 4, which is equal to 2 squared. D equals 3, n equals 3 squared, and so on. This is like all the solutions. And this goes all the way up to until like d squared exceeds 2024. And if you like, you can list all of them. And this works up until like the square root of 2024. So d equals 44 and n equals 1936. That is the last solution. And this gives a total of 43 solutions. Right? It's just when d squared is equal to n. So in summary, what we have so far is that if n is at least 2, then n must be equal to d squared. Now we will address that if n equals 1. If n equals 1, then that's like, if n equals 1, then you need to take exactly one step, right? And that means you need to take exactly one step. That means d is either 1 or -1. In both like cases, you would have made 0 like direction changes. So in both cases, like if n equals 1, then always c must be even. But that doesn't work because when c is even, that must be exactly half the sequences, not all the sequences. So there's no solution. So in total, these are all the solutions. So that means in total there are 43 solutions. So the answer is 43. So in summary, the answer to part A is 36, the answer to part B is 42, and the answer to part C is 43.
That's it for this one. We hope you've enjoyed this problem and its solution. As always, please subscribe to our channel to get updates when we upload. See you guys in the next one!